Hello, everyone. So today we are going to discuss cyclotomic fields, rings of integers of cyclotomic fields, cyclotomic polynomials, and Dirichlet characters towards the end of the lecture. We have already seen in the previous lectures that cyclotomic fields, that is the fields that result from adjoining a root of unity to the field of rational numbers, are very important fields. In algebraic number theory. For example, they play a role in the proof of quadratic reciprocity law. They appear in residues of zeta functions and in partial proofs of Fermat's last theorem. So today I'm going to cover some basics of cyclotomic fields. First of all, we are going to study Q of zeta n, where zeta n is the exponent of 2 pi I over n. This is one of the primitive nth roots of unity in complex numbers. So the element of an arbitrary field K is called root of unity if some power of our X is equal to 1, and a primitive mth root of unity if M is its order in K star. Let me pause a little bit, maybe someone else here, no? Okay, so the word cyclotomic here means dividing the circle, because if you draw your roots on the complex plane, they will divide the unit circle into equal parts, like this, for example. These are roots of unity of order 7. Okay, so first of all, in this section we will construct the cyclotomic polynomial and prove that all the cyclotomic polynomials are in fact irreducible. If n is a natural number, then the cyclotomic polynomial of order n is the following product over all k co-prime to n and less than or equal to n, x minus zeta n to the k. Okay, so on one of the previous lectures we discussed the fact that the cyclotomic polynomial for a prime index is in fact the following finite geometric progression: x to the p minus 1 plus x to the p minus 2 plus and so on plus 1. And we established its irreducibility using sort of an Eisenstein criterion. And it turns out that the corresponding property is substantially less trivial to prove for arbitrary value of n. But first, let us prove that this polynomial is in fact an integral polynomial. The first lemma for today is the fact that for any positive integer n, the polynomial phi sub n has integral coefficients. So to prove that, notice the following fact: if the greatest common divisor of k and n is equal to d, then zeta n to the k is equal to zeta n over d to the k over d, and these two numbers, n over d and k over d, are co-prime. So the corresponding cyclotomic polynomial phi n over d of x is actually equal to the following product over all k, such that the greatest common divisor of k and n is equal to d, and k is less than or equal to n of x minus zeta n to the k. So if we take an index of our polynomial that is the divisor of some of our starting index n, then the roots of this polynomial are also roots of unity of order n. So the set of all k less than or equal to n can be split into disjoint sets of k corresponding to the value of greatest common divisor of k and n. And so the product over all d dividing n phi sub d of x is actually equal to the following double product over all d dividing n, product over all k such that the greatest common divisor of k and n is equal to n over d, x minus zeta n to the k. And due to this argument, this double product is actually equal to the single product over all k less than or equal to n, x minus zeta n to the k. And this, of course, is just x to the n minus 1, because this is a polynomial, this is a monic polynomial of degree n, such that all of its roots are roots of unity without repetition. So it is equal to x to the n minus 1. Suppose that our lemma is not true. Then there is some smallest value of n such that phi sub n of x is not an integral polynomial. Then we have the following product: phi sub n of x multiplied by the product over all phi sub d over d smaller than n and dividing n is equal to x to the n minus 1. Wait a second. Okay. So let me shift this thing. That's okay. So both the product on the left and x to the n minus 1 are integral polynomials. So phi sub n of x is at least a rational function, and it is in fact a polynomial because we know that it is a polynomial over q bar and a rational function over q. So it should be an integral polynomial, well, because these two polynomials are integral. This is
it's a Gauss lemma, yeah?
Yeah. This is a consequence of Gauss lemma. So we will use it, I think, several times today. So here are some examples of cyclotomic polynomials. These two are at least somewhat easy to write down. Phi sub 20 and phi sub 12. Phi sub 39 is a bit longer, and phi sub 87 is very long. And you can also notice that all the coefficients here are plus or minus 1 or 0. This is in fact kind of coincidence, and one of the problems of today's seminar will be devoted to the counterexamples to this little coincidence. Okay, so you can easily check that at least the first two polynomials here are irreducible. So we are going to establish this fact for all n. This is the first theorem for today. All the cyclotomic polynomials phi sub n are irreducible. To prove this, we are going to follow the following strategy. Suppose that f of x is the minimal polynomial of some primitive nth root of unity, w. We are going to prove that it is also an annihilating polynomial for w to the p for any prime p that does not divide n. Suppose that this is not true. Then w to the p has some different minimal polynomial, and f and g are co-prime. So for some integral polynomial, once again by Gauss lemma, you have the following formula: x to the n minus 1 is equal to the product of f, g, and h. Now, as we have w to the p, we are going to consider the reduction of this formula modulo p. We are going to get x to the n minus 1 is congruent to f of x, g of x, h of x modulo p. And then we are going to observe something. First of all, the polynomial on the left is separable in the corresponding field because its derivative is equal to n times x to the n minus 1, and it is not non-zero, so x to the n minus 1 cannot have any repeated roots in the algebraic closure. So now notice the following fact. If we take g of x to the p, then this polynomial has w as a root. So as f of x is a minimal polynomial of w, f of x is divides g of x to the p. Now, once again, by Gauss lemma, or not by Gauss lemma, by some by definition, g of x to the p is equal to f of x multiplied by some t of x. On the other hand, modulo p, we have the following congruence: g of x to the p is congruent to g of x to the p. So every irreducible factor of f of x modulo p is actually a factor of g of x modulo p. So if f and g are indeed different, then x to the n minus 1 modulo p should be divisible by a square of some irreducible polynomial. And this is impossible because, as I said, x to the n minus 1 is separable. Okay? So what we have established here, we proved that if w is any primitive root of unity, then its minimal polynomial also has w to the p as a root for any prime that does not divide n.
And how we used that it's not divided.
What?
It's a separability, yeah.
When we establish the separability of x to the n minus 1. If n is equal to p, then x to the n minus 1 is not separable modulo p, for example. Okay, so let k of x be the minimal polynomial of zeta n. Choose some b that is coprime to n, and repeatedly apply this previous statement to the prime factorization of b. All the primes in this prime factorization are coprime to n. So all possible values of primes do not divide n, so we get zeta n to the b is also a root of our minimal polynomial. But there are phi of n choices for b. So k of x must have phi of n different roots. And the degree of cyclotomic polynomial is exactly phi of n. So k of x is actually equal to phi n of x. And this concludes the proof of irreducibility. In particular, this result can be used to conclude that the extension, the cyclotomic extension of Q is a Galois extension, and its automorphism group is isomorphic to the multiplicative group of the ring Z over NZ. And the isomorphism is given by the following formula. Any invertible element modulo n goes to the following map: zeta n is transformed to zeta n to the a. First of all, why is our extension a Galois extension? Well, it is clearly separable because Q has a characteristic 0. And if we add a single root of our polynomial, say zeta n, all other roots will lie in our extension. This means that our extension is a Galois extension. And this map is an isomorphism due to the following. There are phi of n different automorphisms due to the fact that our extension is a Galois extension. And any possible automorphism should map zeta n to some other root of unity. So for any automorphism, there is an A such that zeta n is mapped to zeta n to the A, and there are only phi of n possible options for A, so all the options are realized. Okay. And you can check that this is indeed an isomorphism, because if you have two different automorphism, sigma and psi, say, and sigma of zeta n is equal to zeta n to the a, and psi zeta n is equal to zeta n to the b, then you can easily check by the fact that this is indeed an automorphism, that sigma psi of zeta n is equal to sigma zeta n to the b, which is zeta n to the ab. So the composition of our automorphism corresponds to the product of the corresponding invertible residues moduli n. Okay. So, for example, the Galois group of our extension is abelian. There is also a sort of universality result for cyclotomic extension that states that if you have any abelian extension of Q, then it is a sub-extension of some Galois, of some cyclotomic extension, I'm sorry. So if you have any abelian Galois extension of Q, it is a subfield of some cyclotomic field. We will not prove this today or anywhere in the course, but it is still a very important statement you need to know about. Okay, so in the next section, we are going to compute the ring of integers of our field. To do so, first of all, let us notice that our zeta n is, of course, an integral element. Denote the ring of integers of our field by O sub n. Then it, of course, contains z of zeta n. Here we are going to prove that these two rings are in fact equal. To do so, we will first reduce, not reduce, we are going to first prove our proposition for the case when n is a power of some prime number. So, first of all, let us take our rational prime p, take principal ideal generated by p in O sub p to the k. Then this principal ideal factors in the following way. You can take pi to be 1 minus zeta sub p to the k. Then this principal ideal is equal to the following power of the principal ideal generated by pi. I have already demonstrated this at the first lecture for the case when k is equal to 1, and here we will generalize the statement. And the power of our prime ideal here is equal to phi of p to the k, or equivalently p to the k minus 1 multiplied by p minus 1. Okay, so first of all, notice that we have the following identity. Phi sub p to the k of 1 is equal to p. Why is this true? This is true because, well, we have our formula for the product of cyclotomic polynomials right here. And let us divide this formula by the first cyclotomic polynomial for n equals p to the k. The first cyclotomic polynomial is, of course, equal to x minus 1. So we are going to get the following identity. X to the p to the k minus 1 divided by x minus 1 is equal to the product of all cyclotomic polynomials of index p to the l over all l greater than or equal to 1 and less than or equal to k. Okay. Now, if you plug x equals 1 to this formula, then what you are going to get on the left? Can anyone please answer this question?
Like by induction, it will be
Wait.
one multiplied.
On the left, I mean.
On the left, we can manually divide.
And what we are going to get?
Polynomials. It will be sum of pay. It will
No, I mean if x is equal to 1.
Because it will be geometric progression.
What we are going to get if
x p to the power of k.
Yeah, we are going to get just p to the power of k. You can deduce this formula however you want. For example, you can use L'Hopital rule and differentiate both numerator and denominator. This is a bit of a funny proof, of course.
But we was getting this result by dividing polynomials, so it's just
of course. This is like correct algebraic proof here. So we are going to get p to the k is equal to the product of all l less than or equal to k phi p to the l of 1. And from this, you can easily deduce, like inductively or somehow else, that phi p to the k of 1 is actually equal to p. For example, you can apply this formula for k minus 1, then for k, and divide one by another. Okay. So we see that the value of our polynomial at 1 is equal to p. So we get the following product. P is the product of all a that are not divisible by p and less than or equal to p to the k, 1 minus zeta p to the k to the a. Now let's divide every factor here by 1 minus zeta p to the k. You're going to get 1 minus zeta p to the k to the phi of p to the k, and you will also get the following product. To prove that the ideals generated by p and by this number are equal, you need to prove that this product is a unit in the ring of integers. First of all, why is this quantity even an integer? This is because here we see just another version of geometric progression. So this is in fact a polynomial of zeta p to the k with integer coefficients. So this is surely integral. Now, how do we invert such a thing? To do so, let us choose b such that a multiplied by b is congruent to 1 modulo p to the k. then trivially you have zeta p to the k is equal to zeta p to the k to the ab, and so the inverse of this ratio is equal to 1 minus zeta p to the k to the ab divided by 1 minus zeta p to the k to the a. And this is once again a polynomial of zeta p to the k to the a. So both this quantity and its inverse are integral, so you have some units here, and so principal ideals generated by p and by our pi to the power phi of p to the k are equal. So this concludes
Why inverse
is integral. Once again, the inverse of this ratio is equal to 1 minus zeta p to the k divided by 1 minus zeta p to the k to the a, correct? Then we have the following identity, and now you should treat your zeta p to the k to the a as a variable, and you get a geometric progression in this variable, which is, of course, an integral element, right? Okay, so this concludes the proof of the fact that these two ideals are in fact equal. What can we also deduce from this proof? From this proof, we get that the ideal generated by pi is actually a prime ideal of norm p. This is because the ideal generated by p has a norm p to the phi of p to the k. So the norm of pi is equal to p. And if we have any ideal with prime norm, this ideal is, of course, a prime ideal. And the quotient is, of course, isomorphic to the simple finite field z over pz. Fine. For the next step, we will evaluate the discriminant of our subring of ring of integers. So the statement here is as follows: the discriminant of this order z of zeta p to the k is equal to plus or minus p to the following power, p to the k minus 1 multiplied by pk minus k minus 1. Okay, how do we prove such a result? Well, of course, the discriminant of this ring is equal to the discriminant of cyclotomic polynomial, because the discriminant of z of alpha is equal to the discriminant of the minimal polynomial of alpha. So we get the following identity. Also, I'm sorry, but in this version of Zoom, this conference will end in 10 minutes, so I guess we are going to get a bit of a break in 10 minutes. Okay, so this discriminant is equal to the following product, product over all pairs of A and B, such that A is not equal to B and AB is coprime to P. So how do we compute this product? First of all, let us fix some A and consider the product over all B. This product is equal to the derivative of the cyclotomic polynomial evaluated at zeta p to the k to the a. To say this, you need to take the derivative of the product and realize that you are going to get sum of certain products, and all the products but one will contain a factor x minus zeta p to the k to the a, and the only product that will not contain it is the product of this form. Okay, is this clear? Okay, so no questions. I guess that's okay. So the discriminant of our ring is equal to plus or minus product over all a coprime to p values of phi prime phi prime p to the k of zeta p to the k to the a. So we take our polynomial, evaluate it at all the conjugates of our primitive root of unity, and this is of course the same as taking a product of all conjugates of the value of our polynomial at our root of unity. So our discriminant is actually equal to plus minus norm of this value. We now need to evaluate this polynomial at our root of unity. So to do so, notice that we have the following identity. This identity can once again be established using our inductive formula. And then you need to take a derivative of this identity, and you are going to get the following the following relation. You're going to get x to the p to the k minus 1 multiplied by the derivative plus some other terms divisible by phi. And this thing is equal to the derivative of the polynomial on the right, which is equal to p to the k multiplied by x to the p to the k minus 1, right? So now you need to plug your root of unity in, and you're going to get phi prime of zeta p to the k is equal to p to the k multiplied by zeta p to the k to the minus 1, which is the same as p to the k minus 1, divided by zeta p minus 1. Notice the disappearance of the power here. This is because the p to the k minus 1th power of our root of unity is actually equal to the primitive pth root of unity. And due to our previous computation, we know the norm of this thing in the denominator in the corresponding cyclotomic extension. So the norm of this zeta p minus 1 in q of zeta p is equal to p. So, well, if p is not equal to 2, so it is equal to plus or minus p, but this does not matter actually. So in our extension, it would be the same thing to the power of the degree of extension. And the norm of p to the k is once again p to the k to the power of the degree of our cyclotomic extension. So we are going to get p to the k multiplied by p to the k minus 1 multiplied by p minus 1 and divided by this. And this is exactly what is said here. Okay? So what we are going to deduce from this, using the fact that that our factor over pi is isomorphic to the field of p elements, we are going to prove the following lemma. For any non-negative integer m, we have the following identity: z of zeta p to the k plus p to the m multiplied by our ring of integers is equal to the same ring of integers. Okay, how do we prove this? Well, for m equals 0, this is a trivial identity because everything here will lie in O sub p to the k, and we have O sub p to the k as a summand on both sides. Every element of our ring of integers is the sum of some element of our ideal and a rational integer. Is it clear why is this so?
No.
Can you explain, please?
I said no.
No. I'm sorry. So this factor is isomorphic to the to the finite field of p elements, and integers 1, 2, 3, and so on, p minus 1 are of course distinct modular pi, right? This is because the smallest integer that is divisible by pi is p, because if some integer is divisible by pi, then its norm is divisible by the norm of pi, which is equal to p. Okay, so you can choose the representative of this factor from the set 0, 1, 2, 3, and so on, p minus 1. So actually, every element of O sub p to the k is the sum of some element of this ideal and one of the following p integers, 0, 1, 2, and so on, p minus 1. Did it become more clear? Petya. Okay, so we have less than 1 minute late. Sorry, we have less than 1 minute.
Нет, Петр Романович, это мы уже перевошли.
Я не знаю, честно говоря. Let's restart once again, okay?